Hey guys, this is video 5. Hope you're still hanging in there. This is going to relate some things that we are just now talking about in class. So we're going to talk about energy for something moving in a straight line as opposed to energy for something moving, rotating. So first, we started talking about work. Work is equal to a force times a distance, cosine of theta. You know that piece. I was being lazy and didn't write it. In order to translate that, we know we're not talking about a force to get something rolling anymore. We're talking about a torque, and we're not talking about a linear distance. We're talking about an angular displacement, or delta theta. And so that's what we would use to find work. Next, we're just going to jump right in. We know that kinetic energy, something that is moving, has kinetic energy, is 1/2 mv squared. We don't talk about mass in terms of rotation, and we don't talk about velocity in terms of rotation. We talk about moment of inertia and omega. And so if something's rolling, it's going to have a rotational kinetic energy, and that has to be equal to 1/2 I omega squared. Not bad. If I'm going to lift something, it's going to have a gravitational potential energy, and that's mgh. If I'm going to lift something that's rotating, it's still going to have a gravitational potential energy, and so it's still going to be mgh. Rotation doesn't affect how gravity is going to work on an object. That makes it easy. We haven't talked about power yet, but power is going to be equal to a force times a velocity. It's also equal to work over time. And this quantity is going to be the same regardless of if it's rotating or not, because work is work. We just might find it differently. But force is going to be translated into a rotational version, which is torque, tau, and velocity is going to be omega. So that's how power is related. So one thing that we have to keep in mind here is that if an object is rolling and moving linearly, so here's my pen rolling across the page, so it's moving a linear distance and it's rotating, it's going to have both a translational kinetic energy, it's moving in a straight line, and a rotational kinetic energy, because this idea of moment of inertia is going to play into how fast something can start rolling. If it has a really uneven mass or a weird moment of inertia, it's going to take more energy to get started, and therefore its velocity is going to move slower by the time we're at the bottom. Now, once they're all rolling horizontally, they're all going to go the same distance because that energy is going to be stored in that moment of inertia. This is why a Prius works the way it does. But it's going to take longer to get started initially. And so if we're thinking about an energy balance equation, which we're going to get pretty good at writing this week in terms of a linear quantity, we have to be able to think about it in terms of both linear and rotation. All right, so you might want to wait to watch this video until we've talked about all of this week, because it will make more sense. But I'm recording it anyway so that you can just jump right in. All right, so it says a thin ring, a hoop, is at the top of a 17 centimeter incline. What is its velocity when it reaches the bottom? We know enough about energy to say that initially this is going to have just potential energy, and then at the bottom it's going to have some velocity, and so it's going to have kinetic energy, but it's also going to be rolling down the hill. Right? And so anytime an object is rolling and moving linearly, we have to say it has both a translational kinetic energy and a rotational kinetic energy. And so our energy balance equation is going to say, well, our initial gravitational energy has to be equal to our rotational kinetic energy plus our translational kinetic energy. That's a T, but it sure looks like an R. All right, so we can plug our equations in. mgh, it's the same, is equal to, and I flipped the equations for these, apologies, but it's equal to our translational kinetic energy, 1/2 mv squared, plus our rotational kinetic energy, 1/2 I omega squared. All right, now pause and go find the moment of inertia for a thin ring or a hollow hoop. All right, you should have pressed play. We have the moment of inertia. It's mr squared. We can plug that in wherever we see the moment of inertia. And that's awesome because that puts mass in every single term. We don't need to know the mass, which is good because we don't have it. So mass cancels. And we're left with this long string of things. And we have a velocity and we have an omega. And that is not helpful. We need, because really we only have a height and gravity. And so we don't know, we're solving for velocity. We don't know radius and we don't know omega. But luckily we have a relationship between radius, velocity, and omega. Go find it on your front sheet. Oh, you found it. It's our tangential velocity is equal to r omega. Well, we don't have r omega. We have r squared omega squared. Well, isn't r squared omega squared going to be equal to v squared? Sure is. And so now we're going to replace r squared omega squared with v squared. And we end up with 1/2 v squared plus 1/2 v squared equals gh. Well, 1/2 v squared plus 1/2 v squared is just v squared. So we get v squared equals gravity times height. We know those values, and so we can plug them in and find a velocity of 1.29 meters per second. So our thin ring, our hoop, hollow hoop, by the time it gets to the bottom of the incline is moving at 1.2 meters per second. All right, you have another problem that you get to try. Pause the video, make yourself do it, see what you can do. If you get stuck, come back. Okay, you should be back. You should have tried this. It says a solid cylinder is on the same incline that's 17 centimeters tall, and what's its velocity when it gets to the bottom? Well, it's going to have the same energies as before. Potential energy is going to be transformed into a rotational and a translational kinetic energies. Same equations, except this time our moment of inertia that we found from the front page is 1/2 mr squared. And so we can plug that in, and again, our masses cancel. That's awesome. And we're left with this relationship again. I did a couple of substitutions at the same time. R squared omega squared. Well, just like before, we know velocity is equal to r omega. So r squared omega squared must be equal to velocity squared. And so we can plug it in. But this time, because I is 1/2, we end up with 1/2 times 1/2, which is 1/4 v squared. So we end up with 3/4 v squared is equal to gh. We know g, we know h, plug it in. Velocity is 2.2 meters per second. Interesting. So we have a lower moment of inertia from the solid cylinder, which means we have less resistance to change, which means it can be moving faster by the time we get to the bottom of our incline. But you say, wait a minute, I know enough about energy at this point to know that that gravitational potential energy should translate into the same velocity. Well, if we let these rings go further to say like out here, that moment of inertia is going to be storing some energy in the solid cylinder or the thin hoop. And so this thin hoop is going to end up moving the same distance in the amount of time that this one moves despite its faster speed because of the moment of inertia. This is what works with the flywheel in your Prius. This is why a hybrid works the way it does. And so we end up getting the same distance, the same velocity by the time they're done here. All right, so that was quick and dirty, but that was energy.